So the single slit means how many slits do we have? One. Okay. So a single slit means we have one and only one slit. Looks like this. Okay, we're going to send some light in like this, right? Now if light were a particle, what would you expect the pattern to look like back here? Just a spot, right? One single spot, and how wide would the spot be? As wide as the opening, right? We would expect the width of that to be the same width as this. However, when they do the actual experiment, what they see, and what you will see, you're going to do this experiment later, what you'll see is that there is a big spot in the middle. However, the big spot in the middle is not necessarily the same width as this. Okay, not necessarily. In fact, as this width gets smaller, this actually gets larger. This one will get bigger. The smaller this gets, the bigger this gets. And then you also see this alternating bright bands, just like before. So again, you see this strange pattern. And again, this would be contrary to what you'd expect if light was a particle. Okay, so let's kind of analyze what's going on here. So if light is in fact a wave, what should happen when it goes through an opening? It should bend, right? What do we call that? Diffraction. So there should be some bending happening. Okay, and when it reaches the back, if light is a wave, there should be some interference. So these are the two wave properties here. Alright, so let's do this one. This one's slightly more complicated to understand than the double slit. I'm going to draw another one down here. Okay, so I'm going to draw one beam like this. I'm going to draw one beam like this. Alright. Zoom in a little bit. Oh, it won't let me zoom. Alright, I'm going to draw a second beam in the middle. Now the two extremes here is going to be this edge right here. This we're going to call L. This one we're going to call L plus 1, which means what's going to be true about the one in the middle? L plus a half. Okay? So just recall from concepts of interference, if I have one wave that looks like this, and I have another wave that travels exactly a half, what happens when they come together? So this would be exactly 1/2, right? When they come together, what do you get? Destructive, or darkness. And if I have another wave that's a full wave farther, what happens when that comes together? Constructive. Okay, now I'm comparing this first one with this third one. They're crest on crest, trough on trough, right? So this full wavelength would be constructive. So recall, that's the key idea, key concept. So let's look at this one. If I send in this beam, let's look at this and this. So this beam at the top and this beam a little bit below it. This is L plus a 1/2. What should happen to those two single beams? They should cancel, right? They're destructive interference. So this beam and this beam halfway should destroy each other. Alright, what if I draw a beam a little bit lower and another beam a little bit lower? So in other words, I have L plus a little bit lower and L plus a little bit lower plus a half. What should happen to this and this? They should destroy again, right? So this should destroy this. And what if I go even a little bit lower still and a little bit lower still? What should happen to those two? They should destroy as well. So in other words, the whole half of the whole top half has a corresponding beam below it, exactly 1/2 wavelength below it, which will also be 1/2 wavelength, which means there's a corresponding beam that will cancel it out. So in other words, when these reach the back wall, what happens? There is cancellation. So right here on the back, there's going to be destructive interference. Okay, that's going to be our first arc. And what's the PD for this? What's the path difference? Path difference is always based on the very top one and the very bottom one. What's the path difference? 1 wavelength. So our PD equals 1 wavelength path difference. Now this is different from the double slit. What happened at 1 wavelength path difference? Constructive interference. It was a bright spot. This time at 1 wavelength, it's actually a dark spot. Okay? All right, let's do another one. I'm just going to draw a whole nother one because this will look a little bit messy here on this. Try to have our comparison here. Now every place in between, like over here, this is still just a bright spot. This is where the first dark spot occurs. Alright, this beam that we're going to take this time, so I'm going to draw 1 and 2. This is going to be L. This is going to be L plus 3 halves. So that would be our PD there. Would be L, would be 3 halves. And I'm going to draw 2 more in between. 1, 2. So what's going to be the distance of this second one? A half. So this would be L, well, L plus a half. And what's going to be this one right here? L plus 1. Okay, now this one's probably the hardest one to visualize. But let's do our best. So we're going to start with this. We're going to start with this one and this one. So this is L and this is L plus a half. What should happen to those two? They should cancel. So L and L plus a half should cancel, right? Because it's a half wavelength difference. If we go a little bit lower, so L plus a little bit lower, L plus a half plus a little bit lower, what should happen to those two? They should destroy. If we go a little bit lower still, what should happen to those two? They should destroy. Okay? Until you get to L plus a half and L plus 1, what should happen to those two? They should destroy. Okay? They're all a half wavelength past each other, they should all destroy. So in other words, think of it this way, the top third is going to cancel out with the second third. So the top third of the beam has a corresponding half wavelength path difference that cancels out with the middle third. Well, what about the third third? What about the last third? If I go to L plus 1, okay, well remember I already canceled that out. So if I go L plus a little bit more than 1, do I have L plus a little bit more than 1 plus a half? No. So the whole bottom third remains. There's no corresponding cancellation for the bottom third. So what you're left with is, well, a relative bright spot. So at this region, we do call this the first bright. In this region, you will have a bright spot over here. Now what's the path difference for this? 3 halves. So the first bright does not occur until 3 halves. And this would be, how would this compare to the central bright spot in terms of intensity? It should be dimmer. Why should it be dimmer? Because mostly the reason it exists is you're getting a lot of cancellation. In fact, 2/3 of it cancels, you're only left with 1/3. So it should be a lot. It should be about 1/3 of what this central bright one is. Okay. All right. So that's the first bright. Where do you think the second dark is going to happen? You could probably guess at this point. Okay. Second dark is PD of 2. What about the second bright? Two bright, PD equals 5 halves. So when you're done, this is kind of what it would look like. Now, notice the central one is much, oops, I drew the wrong color there, didn't I? So here's our first dark. So this is the central bright. This was our first dark from the other page. And you have a large central bright spot, and then it starts alternating. Dark, bright, bright. Okay? Now the equations are the same. So let's just remind ourselves the equations. What's the equation? Tan theta equals, and what's the approximation? Everything's the same. Now there's one slight difference, because what was D called? What was D for double? Distance between the slits. Well, there is no there's only one slit. You can't have a distance between the slits if there's only one slit. Any guesses on what D means? Okay, the width of the slit. So D is the width . D is going to be the width of the slit. Okay, any questions on those? Let's go back to the graph. Let's just do the graph right now. And then we'll do an example problem later. So what I would like you actually to try to do is see if you can sketch this graph. So maybe do it in pencil. See if you can sketch this graph first before I do it. And ideally you do it right underneath. I do want you to make all the dimensions the same. So for the double slit and the grating, when did the first dark spot appear? 1/2, right? Where does the first dark spot appear for this? 1. So notice that in your picture, this is much wider. It's much wider than the grating. But it's even wider than the double slit. So the double slit has this, but the single slit goes all the way to 1. So its central bright spot is much wider. And then where does the next bright spot occur? where does the first bright spot occur? At 3 halves. Okay, now the other difference is, not only that, like, it's kind of spread out a little bit, but remember the intensity, all these intensities are relatively the same, but remember the first bright spot is approximately how much of the original bright spot? About a third. Yeah, so you're going to draw this one like that. Oops, this goes, I drew that wrong. This goes all the way to 2. All the way to 2. Okay, so when you do this out, this should be, if you were to look at this, and you will look at this tomorrow, notice that you have this big bright band in the middle, and then you get your dark spot, and then you have another band of light, and then a dark spot, and so forth. Okay, so notice visually it looks a lot like the double slit, except it's kind of expanded a little bit, where the first dark doesn't occur till 1, and then it alternates. So when this is a bright spot, this is a dark spot. And when this is a dark spot, this is a bright spot, and so forth. Okay? Let's just go ahead and summarize the M values. And actually, you could probably see it here. If you understood this, you could do the M values. So let's do the double slit and the grating. So let's do the path differences. And that's really the key for this whole unit. I mean, once you know the equations, it's understanding which path difference goes with which. So let's do the first dark spot. For a double slit or for a grating, what's the first dark, where does the first dark spot occur? A half of a wavelength. And then where? 3 halves, and so on. Where does the first bright spot occur? Oops. 1 wavelength, 2 wavelengths, 3 wavelengths. What about for the single slit? Where does the first dark spot occur? 1 wavelength, 2 wavelengths, 3 wavelengths. Notice that's the opposite, right? First bright spot occurs at 1. First dark spot for a single occurs at 1. And here's the part where many people make the mistake. Where does the first bright spot occur for a single slit? 3 halves. A lot of people want to just think, oh, it's the exact opposite. It's not quite the exact opposite. Why is it not 1/2? Why can it not be 1/2? Why can it not be 1/2? What's happening at 1/2? It's still the central spot, right? The central spot doesn't end until 1. And so the first bright spot cannot occur until the first dark spot happens. Otherwise, it's just a part of the central spot. And so the single slit, so think of it this way if you want to remember. Just think of where the dark happens. The dark happens a half, the dark happens a whole for the single. The next bright is a half longer. So a half longer than the dark. So the first bright cannot happen until the first dark happens. Got it? Okay, let's do a problem.